This video is going to go over something that we call the root test. So the root test is one way to check for the convergence of a series. So the root test basically says that we are going to take the limit of a series as n approaches infinity. And we're going to take that series, we're going to take the absolute value of that sequence. Then we're going to take the nth root of the whole thing. And this value, after we do our algebra here and take the limit appropriately, it's going to give us some value of L. Okay? So, if L is less than 1, then our series a sub n is absolutely convergent. And we can reach this conclusion if we do our algebra appropriately up here, take the limit as n approaches infinity, and the value that we get is less than 1, then it is absolutely convergent. Our second condition says, if this value L is greater than 1, then our series a sub n is divergent. And we can reach this conclusion again as we do our algebra appropriately up here, and we take our limit, and we get a value L, and L is greater than 1, then it is divergent. Now the third conclusion here is if L is equal to 1, then our test is inconclusive. So it doesn't tell us anything. If L equals 1, then we didn't pick the right method to test for the convergence of our series, and we're going to have to do something else to figure out the convergence. So I do have an example here. Let me see. Okay, so for example, we're given this series, okay? We're going to have n squared plus 1 over 2n squared plus 1. And this whole thing raised to the nth power. So I think one key thing to go over here so that we can understand when we want to use the root test is really the best time to use the root test is when you have a sequence where everything is raised to the nth power. So it doesn't have to be written pretty like this. So it could also be written, let's say, well, this right here is the same as saying n squared plus 1 to the n over 2n squared plus 1 raised to the nth power. It could look, a couple different ways, but generally, if everything is raised to the nth power, we want to use this root test. Okay, so now that we have that established, I will begin my root test down here. So this is the root test. So what we're going to do is this equation right here, that's our a sub n that we see up here. So we are going to go ahead and write it down here, n squared plus 1 over 2n squared plus 1. This whole thing's raised to the nth power. Now to do the root test here, what we're going to do is we're going to take the limit as n approaches infinity of this whole, the absolute value. The absolute value is really important here. The absolute value of this whole thing and take the nth root. Okay? While in this instance, the absolute value isn't incredibly important because everything's positive either way. But in other problems, this absolute value will be very important, and you're going to have to do your algebra appropriately to make sure that you work in the absolute value. But here, everything is already positive. So in this case, the absolute value doesn't change anything. But what this nth root is going to do is it's going to get rid of this this exponent to the nth power, it's going to get rid of it. And so it's going to work out pretty nicely. So this equals the limit as n approaches infinity, n squared plus 1 over 2n squared plus 1. And then when we're taking the limit of a sequence as n approaches infinity, generally the best thing to do is to factor out the greatest degree of n from the numerator and the greatest degree of n from the denominator. So we're going to go ahead and do that. So this equals the limit as n approaches infinity. And then when we factor an n squared out of the numerator, because that's the largest degree of n, we're going to get n squared times 1 plus 1 over n squared. And you can double check that that's correct by multiplying this whole thing by n squared, and you'll get n squared plus 1 by distributing the n squared. So we know we did our algebra appropriately there and correctly. And we're going to pull out an n squared from the bottom as well, because that is also the greatest degree of n in the denominator. So when we pull out an n squared from the denominator, we're left with 2 plus 1 over n squared. And we get that. Again, you can check this by distributing. You'll get 2n squared plus 1. So we know we did our algebra correctly. And now these cancel. Okay, so now I'll write it down here. We're left with the limit as n approaches infinity, 1 plus 1 over n squared over 2 plus 1 over n squared. And then when we plug in infinity, because we're evaluating our limit, we have 1 plus 1 over infinity over 2 plus 1 over infinity. Okay, now a number over infinity is going to be very, 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 very close to 0. So this is equal to 1 plus 0 over 2 plus 0, and that equals 1/2. Well, now we look back up here at our root test, and if L is less than 1, then this series is absolutely convergent. Well, 1/2 is less than 1. We can all agree there. And that equals L. Okay? Or 1/2 equals L, and that's less than 1. Okay, so from this, we can say, therefore, our series of n squared plus 1 over 2n squared plus 1 to the nth power, well, we can say that this series is absolutely convergent by the root test. So just some final remarks here before I finish this up. Generally, when we're doing the root test and we're testing for the convergence of a series, it's going to be best to use the root test when you have a sequence that is raised to, that everything is raised to the nth power. Because if you don't have that scenario, well, then you're going to get some kind of rather tricky algebra steps, and you're going to have to use L'Hopital's rule and all of that. And so it's just going to be easiest to use this. Personally, I would only use this test if you are testing the convergence of a series where everything is raised to the nth power. So that's all for this video.